Good morning, everyone. My name is Jianhong Xia, and I'm from University of Massachusetts at Amherst. Today, I will present our work on flooding attacks by exploring persistent faulty loops. This is a joint work with my advisor, Professor Gao and Ken Fei. So we know that the internet has a lot of components. The router is a very important device in the internet. And if a host wants to send traffic to another host, it will go through a set of routers, and finally it will reach destination. The forwarding path is determined by routing in each individual routers. So in the normal case, and most of the time, if everything is perfect, the traffic can go through to destination, but sometimes the router might not be so smart. For example, here, the host C wants to send traffic to host Y, but the router here, they forwarding the traffic in the wrong direction. So in this case, they have a forwarding loops. If the loops has not been resolved before the TTL value expires, the packet will be dropped, and the end host cannot receive alien traffic from the source. We know that the transient forwarding loops can happen during the routing convergence, but here in this talk, we will focus on the persistent forwarding loops. That means no matter what time, how long you send the traffic, it always have forwarding loops. So maybe some of you want to ask why they have forwarding loops in the internet, and also how it can happen. So here I will give an example. This example just shows that the misconfigurations of pull-up routes will lead to persistent forwarding loops. Here in the left side, this is a network. It has a /16 prefix. So it will announce this prefix to the internet to say that, okay, I own this IP address. Please forward all traffic to this address to my router A. And also the router A, this network has a default route for the local network to access the internet. But actually, /16, this prefix maybe is too large for this network to assign the local host. So it only uses subnet /24 subnet. And if the router A forgot to set up pull-up routes, then all the traffic to the remaining address, that means /16 minus /24, that addresses, they will have forwarding loops between router A and router B, because all the traffic from internet will go through router B to router A, and router A don't know where I can forward this the remaining address, and then it will go through the default route to the internet. So what's the risk of persistent forwarding loops? Here I will give a simple example. Only two routers involved in the persistent loop. For example, the traffic to the address Y, they will have a forwarding loop between router B and router C. So the traffic volume will be amplified between router A and router B and router C. If suppose there is an online bank server X there, and some customers want to access the internet, want to access the bank servers, and all the traffic will also go through the link BC. So in this case, if the link BC is overloaded by the traffic to host Y, then the online bank service will be impacted. So in this case, it is also a denial of service. So persistent loops can lead to a flooding attack to a legitimate host. In this case, they have two kinds of address. We see that one is similar to the address Y. They have persistent forwarding loops. And we call this address is a shadowed prefix. And also another kind of address, just similar to address X, they will impact by the persistent forwarding loops. We call this address is an imperial address. So our work wanted to answer the question, in the internet, how many addresses are shadowed prefix in the internet? And also, how many addresses that will be impacted by the persistent forwarding loops? So to answer these two questions, we did an extensive measurement in the internet. And we sampled 2 addresses in each /24 IP block. Because we know that not all IPv4 address has been assigned in the internet. So we just collect the routable address from route view routing table. And also deaggregate all the prefix into a /24 prefix. Because sometimes in the routing tables, they have a /8, /16, a very large IP space. Then we just deaggregate it into the /24. And here we got all this /24 prefix as a fine-grained prefix. So our measurement is that we do trace routes to each /24 prefix and sample 2 IP addresses. So finally, we have traced almost 5.5 million fine-grained prefix. And this measurement is a very long time, lasted for 3 weeks in last year. So here's the result. We found that almost 2.5% of routable addresses that have persistent forwarding loops. And also, almost 0.8% of routable addresses will be impacted by these persistent forwarding loops. We also look at where these IP addresses are in terms of the autonomous systems. We found that all these IP addresses are widely spread in the multiple autonomous systems. So maybe you guys may ask, maybe this is the only particular special case from your observation points, or maybe it's a special case to that particular IP address you sampled. So to validate the persistent forwarding loops, we also did the same experiments from the multiple locations, from the Asia, Europe, Western and Eastern coast. And we found that 90% of shadowed prefix that still have persistent forwarding loops from the multiple locations. And for each /24 prefix, for each /24 prefix, we also sampled about 50 IP addresses to verify that whether it is because of the only sampled 2 IP addresses in our experiments. So we found that almost 70% of shadowed prefix show that all additional sampled IP addresses still have a persistent forwarding loops. So this validated that the persistent forwarding loops really exist in the internet. And also it will impact a lot of routable IP addresses. So we will look at the property of the persistent forwarding loops. First, we want to know how long, that means how many routers involved in a persistent loop. From our result, we found that 86% of forwarding loops that have 2 hops alone. And some of them has more than 15 hops long. That means more than 15 routers involved in a loop. And 0.7% of the following loops that have more than 10 hops. But the majority are only 2 hops long. And also we look at the location where these persistent loops happen. We found that when we do trace route to the deceleration domain, and about 82% of following loops that happened within the deceleration domain. So this implies that because the loops happens within deceleration domain, so means that no matter where you do trace route or no matter where you observe these following loops, you can always observe the following loops from the various locations. And also, it amplifies the traffic in the following loops significantly. So, to understand where these following loops and what ISP will be impacted by the following loops, we classify the persistent following loops into 3 categories. The first one is following loops happen within one autonomous system. We found that 94% of following loops in this category. As I mentioned earlier, only 82% of following loops within destination domain. So that means they still have some loops happened in the middle of the network in the following path. So that means it might be in the core of network or in the network that among A is passed that before reach to destination. And also the second category is that we classify the persistent following loops into 2 autonomous systems that will be involved. We found that 5% of the following loops in this category. So it's more likely the following loops happened in the boundary of an autonomous system. And the last one is that we found that only 0.4% of following loops that involved by more than 3 or more autonomous systems. We also found that some following loops that are involved by 7 or 8 autonomous systems. So it really, the impact is really large. So here I will show several examples where the following loops happen. So this is an example that the traffic to this address. So please don't do trace route to this address at the same time. Otherwise, it is really a flooding attack. We will also show several other addresses that have following loops in the following slides. In this example, the following loops happened in the MAC path networks. And the following loop is within this network. So we think that it might be a misconfiguration in one router in this network. And the second example is that the following loops happen within 2 domains. And you see that from the trace route, we see the following loops within happen within UUNet and NDT America. We also verified from the DNS name of these 2 routers, and it looks like the misconfigurations on the one for boundary router in these ISPs. And I will focus on this example. This example, they have 4 autonomous systems involved in these loops. There is Here, the WCG is a William Communications Group. And the clear sky, I can see the broadband network in the United States. And VSN is a network in India. And Savage is a large ISP, is a provider of the VSN. So the traffic, once the traffic to this address, it will go through, depends on where the traffic enter to these loops. Here it will go through William Communications and then reach to Clear Sky. And Clear Sky forward traffic to the India and then go back to the Savage and then go back to the William Communications. There are almost 17 routers involved in this persistent forwarding loop. And we also did a more detailed investigations on this case. We found that WCG is a provider of a Clear Sky. So all traffic to the Clear Sky will go through WCG and then reach to Clear Sky. And this IP block /22 IP blocks was owned by Clear Sky. So it announced to the internet that, okay, all traffic, please send back to me. However, Clear Sky just assigned half of address in locally. For example, they just assigned 2/24 address in the locally, and also assigned 2 other /24 address to VSN in India. And VSN in India only use one of /24 locally. And then they don't have a pull-up routes. So they have a default routes, or they have a default routes to its provider service. So it turns out that all traffic to the 72.9.94.0/24, this address, the traffic will go through WCG and Clear Sky, and then forwarded to the VSN in India, and then go through default routes to Savage. So from this example, we found that although they are small, they have misconfigurations in a small network, but the Tier 1S or backbone network will be impacted because the forwarding loops will cross to the multiple autonomous systems, even to the international link. Because we found that from Clear Sky to the VSN, they will go through an international link. So that means if someone sends traffic to overload the links in the forwarding loops, Tier 1S and large ISPs will get denial of service if the link is flooded. So to understand how many of Tier 1As and large ISPs will be impacted by persistent forwarding loops, we look at the routers in the loops and use the DNS name to resolve it. We found that all Tier 1As will be impacted. And from here, we see that Unet, AT&T, Sprint, ARL, Level 3, and Quest, all these large ISPs will impact by the persistent forwarding loops. We also look from the DNS name of the routers, we look at the distribution of the countries, how many countries will be impacted. And we found that more than 120 countries will be involved by this flooding attack. So to understand how large the flooding traffic will be amplified in the forwarding loops, we just use a typical case to calculate amplifications of the flooding traffic. Here if attackers want to do attack to flood the links, they will send the traffic with TTL value, initial TTL value as large as possible, suppose 255. From our data, we found that normally trace route will pass 14 routers to enter 14 loops. And the most of the case, the 14 loops has only 2 hops long. So in that case, we can simply calculate that it will amplify the traffic 120 times. So here we just estimate that how easily the attacker can overload the link. Suppose the available bandwidth of the link BC is 100 Mbps, and the number of compromised machines is 25. We know that it might be more if they use a botnet, and they have more compromised host. So the average traffic need to overload the link is almost 33 kbps. So it is feasible, quite easy to get this rate. Okay, only for even for the loop that have a long loops, even for long loops that have 16 hops, these still can amplify the attacking traffic about 15 times. So since the flooding attack exists in the internet, and misconfigurations of pull-up routes can cause the persistent falling loops. Here we want to verify that how many of persistent loops are caused by the pull-up routes. Here we have a simple heuristic to validate the pull-up routes misconfiguration on pull-up routes. Here we think that to a destination domain, if the some traffic, some trace route, they can reach to destination, but some they have falling loops. If these two traces they share the router inside in the destination domain, so we consider this case is a pull-up route. And from our result, we found that almost 70% of persistent loops are caused by misconfiguration of pull-up routes. So here is the summary. The first is that persistent loops do exist in the internet, and it's also a large number of routable addresses have persistent falling loops. And also it will affect a lot of legitimate hosts. And also all these addresses are widely distributed in the internet. Also the flooding attacks can be launched from the multiple locations. And because it can amplify the flooding traffic in the link, so it will affect the link and any ISPs that are involved in the falling loops. Finally, we found that all Tier 1As and large ISPs will be impacted if someone launches a flooding attack using persistent falling loops. So that's all. Thanks.
Yeah. Jared?
Jared Mach, NTT America. There was one loop that was listed that you claimed was with one of our customers. I did not follow your instructions in not trace routing to it. It turns out to be a customer that we transferred to some other provider, but the link DNS, their serial IPs were not renumbered. So it's actually a customer of some other provider. I went and let them know about that. But in addition to that, there is a question in my mind of, you found some of these. Is there a list of these that you can share with the operators. You may not want to put them on a web page because people might exploit them. But have you been sharing them with operators such that they can look into them and attempt to fix them?
Right, yeah, we don't share any information to the outside. And of course, we will do some surveys and contact operators about the faulty loops we have found.
Okay.
Well, if that's it, we can move on to the next talk.